Thank you for joining us, our most valued audience. Today, we want to continue our discussion on two-way analysis of variance. Yesterday, we began officially discussion on two-way analysis of variance when we had elaborate introduction on two-way analysis of variance. Today, we want to solve a real-life example on two-way analysis of variance. And then the question is what we have here on the board. The experiment we have on the board is an experiment that concerns two factors. And these two factors are the temperature and then the catalyst. And then the question of interest here is that we should conduct the two-way ANOVA tests. And of course, we should remember that in two-way analysis of variance, or in general in ANOVA, the interest is to know if there is any statistical significant difference in the mean levels coming from what? From the factor. For instance, here is a temperature, which of course is what is a factor. And this temperature has three levels. The three levels are 25 degrees Celsius, 50 degrees Celsius, and 75 degrees Celsius. And our interest here is to know if there is any statistical significant difference in the means of these observations coming from 25 degrees, coming from 50 degrees, and coming from 75 degrees. By implication, we are going to compute the mean coming from this first level, 25 degrees Celsius, have the value, compute the one coming from 50 degrees Celsius, have the value, compute the means of the one coming from 75 degrees, have the value, and be able to see if these three values computed for these three levels of the factor, temperature, any of them is going to be statistically different from the rest of what of them. The same thing applies when we come to catalyst. Catalyst has what? Four levels. Catalyst 1, 2, 3, up to 4. So we are going to compute the mean coming from catalyst 1, compute the mean for catalyst 2 down to catalyst 4, and be able to see whether these means computed from these levels of catalyst, any of them is going to be statistically different from what the rest of them. And then, of course, for us to conduct this test, we are going to begin by stating the hypothesis. And of course, the null hypothesis of any ANOVA test is trying to say that the factor of interest doesn't have effect in the observations. How do we mean by this? If the mean of these observations at least 25 degrees Celsius happens to be the same thing as the mean of these observations coming from 50 degrees Celsius, and equally the same as the mean of these observations coming from 75 degrees Celsius, it can quickly be concluded that temperature doesn't have effect in these observations, because increasing the temperature from 25 degrees down to 50 and down towards 75 didn't have effect in these observations in terms of either increasing their values or decreasing their values. And then in that case now, you are trying to say that the mean of that of 25 is the same thing as the mean of that of 50, and is the same thing as the mean of that 75 degrees Celsius. That is what null hypothesis is trying to say. So I will begin by stating the hypothesis as a way of providing solution to this question. So I have solution. And that solution begins by providing or stating the hypothesis. For me to state the hypothesis, I'm going to say that H subscript 0. Of course, this H subscript 0 is what is traditionally known as the null hypothesis. And you are saying what? That mu This mu you are writing here is, as you are saying, the mean of the population of observations now under the 25 degrees Celsius. So you put here 25 degrees Celsius is equals the mean for 50 degrees Celsius, for 50 degrees Celsius, 50 degrees Celsius, and then is equals what? The mu for 75 degrees Celsius. So by implication, you are saying that the means of all of them are the same thing. Against the alternative, an alternative hypothesis, of course, is any hypothesis that contradicts the null hypothesis. So you are now going to say verse, that is against, that h subscript 1. This h subscript 1, of course, is our alternate hypothesis. Then we have that what? Mu I is not equal to what? Mu j. For I is not equal to what? J. And of course, what we mean by this statement is that the mean of a particular level is not equal to the mean of the other what level. Where this I can be this 50 degree, 25 degrees Celsius, and J can be 50 degrees Celsius. I can still be 25 degrees Celsius, while this J be 75 degrees Celsius. I can equally be 50 degrees Celsius, while this J becomes what? 75 degrees Celsius. So if the pace of any of these means are not what? The same thing, of course, you have already contradicted this null hypothesis, and that's what we call the alternate hypothesis. So this is how to state the hypothesis now for that factor called what's called the temperature. And of course, the moment we state the hypothesis now, we talk about the level of significance. So, and the level of significance they ask us to use here is, or the level of significance we should be using here is 0.05. So I have that my alpha, which of course is level of significance, is 0.05. And the moment we are done stating the level of significance, the next thing is for us to state the test statistic. And of course, our test statistics in ANOVA is an F calculation, or what we call F cal, because it follows F what distribution. So how to state it is that our test statistics now F cal, which of course is what we are calling F calculated, is given as what? M S of A all over M S of what? Of E. I will explain what time. Of course, this thing follows F of what? A minus 1, comma, of A minus 1 into B minus 1 at alpha, which of course is 0.05. I will explain what we mean here. In this test, I am going to call this my temperature factor A and call this my catalyst factor B. So meaning that what I mean here by MSA is mean square of factor A all over mean square error. That is what we call our F cal or F calculated. So the moment we define our test statistics, the next thing is for us to state the critical region. So to state the critical region, of course, the critical region is the region at which when the test statistics falls in, we are going to reject our null hypothesis. And to state it, we say that F cal greater than what? F of alpha at A minus 1, comma, A minus 1 into B minus 1, reject the null hypothesis. Reject H0. Otherwise, we accept it. So these are the steps that we are going to follow when we want to conduct this test regarding this temperature. First of all, we state the null hypothesis, which is this. Secondly, we define our level of significance, which is this. The third one, we state what we call the test statistics, which is this, and it follows F distribution. And then the third, we are going to define our critical region. Here, what we mean is that after we have computed this, we get a F cal. We are going to read this value from a table, and if this value which you have calculated happens to be greater than the value we are going to read from the table, we are going to reject the what? The null hypothesis, which says that the mean of all the levels are what? Equal. And then we go for the alternative that says that they are not equal. That is how to state all about the temperature. We are equally going to clean this and then state the steps now for the catalyst now before we now go into our computation of the test statistic. So permit me to clean here. I'll be fast about that. Okay, so we now go and talk about how we can state that of the catalyst. The same procedure that we use while we are doing that of temperature is what we are going to do here. You are saying that when you get the mean here, you get the mean down here, get the mean down here, and get the mean down, that all these means are going to be the same for the null hypothesis. And in that case, you have implied that catalyst doesn't have effect in this because the catalyst 1, the catalyst 2, the catalyst 3, all of them arrive at the same means. So they did not affect these observations in terms of either increasing it or decreasing it. And that in that case, you are going to say that your H subscript 0, H subscript 0, they are going to say that mu1 is equals what? Mu2, which is equals what? Mu3, and which is equals what? Mu4. Okay? The population means of these of observations under these levels of catalyst now, that all of them are going to be the same thing. Verse, then you have H subscript 1, that mu of I is not equal to mu of what? J, such that what? I is not equal to J. So if you pay any of these observations, and then their means happen not to be equal, of course, you have contradicted this null hypothesis. Even if it happens to be only this one and these two, you are already contradicting the sign of this null hypothesis. Okay? So we now go ahead and state our level of significance that alpha is given as 0.05. And then we go ahead and state the test statistics now, which of course still remains our F cal is given as M S of what? Of B, all over what? M S of what? Of E. You are talking about mean square of factor B, which is catalyst, all over mean square of error. And it follows F distribution with alpha level of significance and A, B minus 1, A minus 1 into B minus 1. Do remember that in the first one, we called here A minus 1, and here we are talking about B minus what? 1. Then our critical region becomes what? That our F cal greater than what? Our F of alpha of B minus 1, comma, of A minus 1, and then B minus 1, we are to reject H0. Reject H0. So this is exactly what we are going to do. So we state the level of the hypothesis, step 1. We define the level of significance, step 2. We define our test statistics, step 3. Then we define our critical region. Then the next thing that we are going to make a conclusion depending on the values of this our F cal and this our F tabulated coming from the table. So we are quickly going to clean this board now and then go into the computations proper. So permit me to clean this. Go into the computation. And it is good that I remind us that when we talk about what computation in this kind of a test now, it is better that we define our ANOVA table. So that whatever value we get now, we are going to put inside that ANOVA table. And how to define the ANOVA table of two-way ANOVA is this. I did say it in our introductory class, so you can make reference to that class because it was detailed and it will go a long way to making you understand the lecture better. So we have what we call our S.V. Our S.V. Yesterday we say that our S dot V is what we call source of variation. Then we have what we call our DF, what we call our degrees of what of freedom. Then we have what we call our SS. SS is what we call sum of what square. And then we have what we call MS, what we call the mean square. And then we have F, what we call the F ratio. F ratio. We call it F ratio. This is what we have there. So we underline. Then we now underline here. Now we have to, here is source of variations. So, and then we have two factors here that can introduce what? Variation into these observations. So, meaning that this first temperature, now this temperature here, permit me, like I said earlier, to call it what? F of what? Of what? A. F of A here, I mean, is what? Is factor A. Then I have what we call F of what? Of B, what we call factor B, making reference to the what? To the catalyst. I have what we call our error, then, and I have what we call our total. What we call our total. Then we come over to degree of freedom. To determine the degree of freedom for factor A, we said it in our class yesterday, we are going to make use of a formula that says A minus 1. And the question is, what do we mean by A? What we mean by A is the number of levels of what? Of factor A. Here is our factor A temperature. Let us count the levels. 1, 2, 3. So there are 3 levels of what? Of factor A. And this formula says A minus 1. So A minus 1, 3 minus 1 is going to be what? 2. So the degree of freedom for factor A is what? Is 2. Then we come over to the degree of freedom of what? Of factor B. The formula is B minus 1. And B, of course, is the number of levels of factor what? B. We count the number of levels. 1, 2, 3, 4. Okay? So, which means here becomes 4 minus 1, which becomes what? 3. The next thing is for us now to get the level of degree of freedom for what? For error. The formula is A minus 1 into B minus what? 1. Here we had a 3. 3 minus 1 will give us what? 2. Here we had a 4. 4 minus 1 will give us what? 3. And then 2 times 3 will give us what? 6. So the degree of freedom for error is what? Is 6. And then the last but not the least is what we call our degree of freedom for what? For total. And the formula is given as what? AB minus 1. Our A is 3. Our B is 4. 3 times 4 will give us 12. Okay? Minus 1 will give us what? 11. So here I have what? 11. And I said it yesterday while we were having the introductory class that oftentimes we are given the degree of freedom for total. We might be given that of error. We might be given that of factor A, and we are required to find that of the factor B. If it happens that way, you remember what we told ourselves yesterday, that the degree of level of DF of total is equal to DF of what? Of A, plus DF of what? Of B, plus DF of what? Of error. That is, degree of freedom for total is the sum of degree of level of what? Of factor A, that to that of factor B, and to that of what? Error. If you come here, you see that 2 plus 3 will give you what? 5, and 5 plus 6 will give you what? 11. So assuming you are giving this 11 here, you are giving this what? 3 here, you are giving this 2 here, and you are not giving this one. What you do is to say 2 plus 3, it will give you 5. 5 minus 11 will give you what? 6. So anyone they are asking you, you make use of what? Of this relationship. Then we now quickly go to our sum of squares. Okay? So you permit me to clean here. While we go to sum of squares, permit me to clean this place. Okay. For us to obtain the sum of square, we are going to use this formula. We have what we call sum of square for factor A and sum of square for factor what? B. So that's what we call SS of A and SS of what? Of B. For us to get SS of A, the formula is that SS of what? Of A is given as sum over what? I of yi dot all squared minus what? Y dot dot all squared all over what? AB all over what? Over B. I will explain what we mean by this. Now, we coming to this data, I can do something like this. I can introduce a line this way. I can introduce a line this way. I can have a line this way. When I have line this way, I can come here now for me to get the sum of all these observations under this level of what? Factor 25 degrees. I am going to say 25 plus 28 plus 22 plus this. I will report here. As I'm summing this observation, this 25 degrees Celsius is constant. It is not changing. What of course are changing are the levels of what? Of factor B. So, and in ANOVA, we use dots to show that we have summed observation over a range. The range here is beginning from 1 to what? To 4 that I'm summing these observations. So I am going to have something that looks like this, where I call this one my yi dot. Yi dot. So if I sum this observation from what I have here, the sum of all these observations is what? Is 99. So here is 99. The sum of all these one is what? Is 102. And the sum of all this one is what? Is 117. That is what I have there. The same thing applies here. I am going to sum these ones here, summing them this way. And if I'm summing them this way, it's better I do something like this. And I'll write what? Y dot what? J. Why do I do y dot j? If you come here, as I'm summing these ones now, this level of catalyst 1 remains constant. What are now changing becomes the levels of this first factor called the temperature. And of course, when I sum these observations now, it is over this thing that is changing, and that's why I'm using dots to represent it. Because here, if I write Yij, this I stands for what? The first factor, temperature, and this J stands for the second factor called catalyst. Okay? So in that case now, I am now going to sum this one. If I sum this one, the answer here they have is what? Here is 82. If you sum this one, you get what? 89. If you sum this one, you get 71. And if you sum this one, you get 76. Now, I can decide to sum this one from here to here. I can decide to sum this one from here to here. The answers are going to be the same thing. But the good news there is that if I am summing this one, you find out that this dot becomes constant. What will be changing in this I, which are these levels of what? Of this factor. So here becomes y dot dot, because both of them now are now going to be dot dot. The total here is what they gave as what? 318. I will make explanations here. This 99, 102, and 117 are what we call the group means. Because this is group 1 for 25 degrees Celsius, group 2 for 50, and group 3 for what? For 75. But this 318 is what we call the grand total. Because you have summed all these group means together. By implication, you have summed all these observations in this data set. The same thing applies to this 82, 89, 71, and 76. They are called the group totals. With respect to what? To catalyst. Why this one becomes our grand total as well. So if you come here, when you talk about yi dot, you know you are making reference to 99, 102, 117. And of course, you are saying all over B. And this all over B now is telling you sum this thing over what? Over these levels. And they are 4 in number. So this B now is talking about what? 4. So meaning that you know what B is. You know what A is because A is 3. 1, 2, 3 here. Then you know what yi dots are, which is this. You know y dot dot, which is 318. So for me to get this this SSA now, I will now say therefore my SS what A now is given as the first one here is what? 99 squared all over what? 4 plus. The second one is what? 2 all squared all over what? 4. The third one is 117 all squared all over what? 4 minus. Here becomes my what? 318 all squared all over. Here is 4 times 3 times 4, which becomes what? 12. If you evaluate the whole of this, the answer you are going to get for that SS of A is 46.5. You can decide to cross-check it to know. So in that case, you come here and you put what? 46.5. You have your 46.5. You quickly go over to that of SS of B. So I'm going to clean here and we talk about SS of B. Of course, you have seen this formula. You have seen the computation I did here. So you permit me to clean here while I talk about SS of A. So I'll clean here. I'll talk about SS of B, sorry. So if I'm talking about SS of B, I'm going to say that SS of what? Of B is going to be now sum over what? J of y dot what? J all squared all over what? A minus y dot dot all squared all over what? A what? B. That's what I'm going to do. So this time around now, I'm interested in factor B. And then that's why now what I should be considering this my 82, 89, 71, and 76 because they are the one talking about what? Y dot what? J. And it's y dot j that I have here. Okay? So what I'm now going to do now is this 9 is equals. The first one here is what? Is 82. So I have 8 what? 2 all squared all over. Here is now all over A. Talking about the number of levels of factor A, which is 1, 2, 3. So all over 3. Here it becomes what? 8 what? 9 squared all over what? 3 plus 71 all squared all over what? 3 plus 76 all squared all over 3 minus 318 all squared all over 3 times 4, which is what? 12. And if you evaluate all of these things, what they gave it to be is 60.3. So here is our 60.3. You can cross-check this because you already know what we are doing. So I'll quickly come here and write 60.3. Okay? Then what I'm now going to do now is to skip now and talk about what? SS of what? Of T and give you the formula here. So you permit me to clean this and I talk about SS of T, which is sum of the square total. So permit me to clean here. Cleaned. So when you talk about SS of T, the formula is SS of T is equal sum over Ij Yij all squared minus y dot dot all squared all over what? AB. I will explain. This Yij stands for all these individual observations in the data set. So this time around now, when I want to solve now, I'll be making reference to 25, 28, 22, 24, 27, 29, 23, 23, 30, 32, 26, and 29 before I subtract this. So this thing becomes, this equals. The first observation is what? 25 all squared. There is nothing like all over here, plus. The second observation is what? Is 28 all squared plus dot 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 plus. It's assumed that this dot 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 covers from this 22 to 24 down to 32. The last two becomes 26 all squared plus 29 all squared minus. I now come to here, which becomes 318 all squared all over what? 12. If you evaluate this, the answer they gave it to be is that this is equals to what? 111.0. So we quickly come to this total and write what? 111.0. And there is something I want to say quickly, that there is a relationship equally that exists about sum of squares. They say that SS of total, that SS of T is equals to SS of what? A plus SS of what? B plus SS of what? Of E. That sum of square total is equals to sum of square of what? Of factor A plus sum of square of factor B plus sum of square of error. So by implication, if you are given that of factor A, you are given that of factor B, and you are looking for this and they are giving that of total, you say this plus this. If you subtract it from this place, you'll be able to get here. So by making use of this relationship. So anyone that is missing, you use this relationship to complete it. And if you do that, they gave that our SS of error is 4.2. That this is 4.2. By implication, that if you say this plus this, subtract it from this, that you are going to get 4.2. That is what we need to know about that. Okay? So you permit me now to clean this place. Okay? And then we now talk about what mean square. I'll quickly clean here, talk about the mean square. When we talk about the mean square, the formula for mean square is the sum of square all over degrees of what? Of freedom. So if you want to talk about ms, if you talk about ms of what? A, that is mean square of factor A, the answer is ss of A all over what? A minus 1. This A minus 1 is degree of freedom for what? For factor A. And the answer is equals. We got our SS of A to be 46.5. So here becomes 46.5 all over. Remember, there are 3 levels of what? Of this factor. Minus 1, we have 2. That was why we have 2. So here becomes what? All over 2. So if you say 46.5 divided by what? By 2, it is approximately 23.3. So we have approximately 23.3. You can try to confirm that. And if you talk about ms of what? Of B, it becomes what? ss of B all over what? B minus 1. And our SS of B is 60.3. So this is equals to 60.3 all over. Then our level of factor here, there are 4. 4 minus 1 is 3. That's why we had 3 here. So is it all over 3. This is equals. The value which they got it here is 20.1. So we have our 20.1. That's the value we have it there, 20.1. So we now quickly talk about the MS error, that is the mean square error. Okay, the mean square error here is MS what E is equals SS what E all over. Degree of freedom for error, which we said here, is 6, and it is obtained by, we have A minus 1 into B minus 1, which is equals to, our SS error is 4.2, so we have 4.2. Remember that the level here is 3, the level here is 4. 3 minus 1 is 2, 4 minus 1 is 3. So we'll be able to have our 2 times 3, which is this 6 we have here. So we say all over what? 6. And the value which they have here is 0.7. So here is a 0.7 and here is 20.1. So we don't have anything like a mean square total. So we just have a column here under mean square total. Then we quickly now go over to F ratio. So you permit me to clean here. Talk about F ratio. Talk about F ratio. Talk about F ratio. So when you talk about F ratio, I am equally going to talk about F ratio with respect to the 2 factors we have. Okay? So our F ratio now is going to be F ratio for factor A now is given as, we have ms of what? A all over ms of what? E. So for me to get the F ratio, which of course is what we are calling the F curve for A, it is the mean square of factor A all over mean square what? Error. And my mean square for factor A is 23.3. So this becomes what? 3.3 all over. MS of error is 0.7. So this is 0.7. And then what they got it here to be is 33.3. You can decide to press your calculator. 33.3. Okay? Now, we now talk about the F ratio with respect to catalyst, which is our factor B. So we have F ratio of what? B is given as what? M S of what? Of B, all over what? M S of what? Of L. B is equals. Our M S of B is 20.1, so this is 20.1 all over. Then our M S for error is 0.7. This is 0.7. The answer which they have here about it is 28.7. So you can decide to cross check 28.7. So I'll call the values up here. My F ratio here now is 33.3 and it is here 28.7. Okay? So these are our F ratios, which of course we are calling our F cal. What are we going to do next? What we are going to do next is for us to go and get the value of F tabulated from the table. F tabulated. Remember that for the factor A, our F tabulated is going to be gotten like this. We are going to have that our F for that of A of 0.05, because the formula is coming from F of what? Of alpha of A minus 1, comma, A minus 1 into B minus 1, which of course becomes our F. Our alpha is 0.05 that we are using, 0.05. My A minus 1, A is 3, so 3 minus 1 will give me what? 2, comma. 3 minus 1 will give me 2, 4 minus 1 will give me 3. This time this will give me what? 6. So this is degree of freedom for factor A, degree of freedom for error. And reading this thing from F distribution table, the value they gave there is 5.14. This is 5.14. Then we quickly do the same thing for factor B. We heard that this is F of alpha of B minus 1, comma, into A minus 1 and then B minus 1. This becomes our F. Our alpha is 0.05 as usual. Then coming to here, this is B and B is 4. 4 minus 1 will give me what? 3, comma. This one still remains what? 6. And the value which they give here is 4.71. 4.71. Having succeeded computing all these things, what can we say with respect to whether this temperature and this catalyst have effect on these observations? Do remember that we gave a critical region. The critical region which we gave is, you are going to permit me to clean here so we can record the critical region now and then make a conclusion here about it. So permit me to clean here. Remember that the critical regions which we gave is that F cal, which we call that F cal greater than what? F of alpha of A minus 1, comma, of A minus 1 into B minus 1. We should reject KH0. Reject KH0. So we ask ourselves, what is our F cal for factor A? Our F cal is this thing we are calling F ratio here, which is 33. So we now have what we call, here becomes what? 3.3. Then of course, this our F tabulated is what we got here, which is a 5.14. So we have 5.14. We ask ourselves a question. 33.3 compared to 5.14, which one is greater? It's clearly seen that 33.3 is greater than 5.14. And when it is greater, we are to reject what? H0. And H0 say that temperature didn't have in the observations. So when we reject H0, what do we say? We go for the alternative. Alternative say that temperature has effect. So we are now going to conclude in this, our experiment, with respect to temperature, that temperature actually has effects on these observations. So for that reasons now, there is a statistical significant difference in the means of these levels of what? Of temperature running from 25 down to 75. Then we quickly go over to that of our factor B. Factor B says that our F cal He said that our F cal greater than what? F of alpha of B minus 1, comma, into what? A minus 1 into B minus 1. That we should reject H0. Reject H0. So we ask ourselves, what is our F cal here? Our F cal here is 28.7. Our F tabulated now is this value which we got here, which is a 4.71. So we now say when 28.7 is compared with 4.71, which one is greater? Of course, 28.7 is greater than 4.71. And when the sign is greater, what do? We reject H0. And what is H0 saying? That these catalysts do not have effect on this. These different catalysts, catalyst 1, catalyst 2, catalyst 3, catalyst this, that no any value of catalyst there doesn't have this affect these observations. That is what H0 is saying. But we are now rejecting this H0 because this 28.7 is greater than 4.71. And when you reject it, you go over to the word for the alternative. And the alternative is saying that there is a significant what difference in the mean levels of these different catalysts, which in implication says that this catalyst has a significant effect on these observations. That is how to make a conclusion and conduct a two-way analysis of a variance test. We should bear in our minds that this two-way analysis of variance which we conducted here is the type without interaction effects. We are just interested in the effect of the two factors, temperature and the catalyst, not necessary on the interaction effect of temperature and catalyst combined together. So this is how to go about this. Then let me now refresh your mind again once more with regard to this table, ANOVA table. Now, seeing what we have here, it can be understood that somebody can come and clean this 33.3, clean this 60, clean this 2, and give me an ANOVA table this way and ask me that I should complete the missing observations, or what we call the missing value. It is easy. It is easy because I have known that for me to get my mean square error, that the answer is sum of the square, this is mean square. If you want me to get the mean square for factor A, the answer is sum of square of factor A all over degree of freedom. So if you have cleaned here and you're asking me to find the value that is here, I am quickly going to say this 46.5 divided by 2, I will get the value that is here. Or assuming you have given me this and you have given me this and you want me now to find this, the same thing applies. I will now know how I'm going to navigate my way. Because since I know that this all over what is here is what will give me here, I will now be able now to make that equation and find the one that is missing. The same thing applies to this, the same thing applies to any of them and the rest of them. Because for us to obtain the mean squares, it is sum of squares all over the respective degrees of what? Of freedom. For us to get the F ratio, it is our mean squares all over what? Mean square of errors. So if you did not give me this, what I'm going to do is this all over this. I will now have this. I will do, if you did not give me this, what I'm going to do is this all over this. I will now get this. If you did not give me this, I will do this all over this to get this. So that is how to go about completing the missing observations now from the two-way ANOVA table. Thank you for your audience. I still plead with us that we stick around our classes as we continue to make sincere efforts in bringing some of these things that are concrete to a very good understanding of our audience. Thank you for today and see you in our next class.